Hello and welcome. My name is Richard Taverner and I'm your host of Any Further Questions. This is the fourth in a series of 6 special episodes where I sit down with Chris Lintott, our current Gresham Professor of Astronomy, following each of his lectures to ask him all the questions from our audience that we didn't have time to get to. The series is called Discovering the Universe, and this time he'll be answering questions from his lecture Pulsars, Microwave Ovens and the Radio Sky, which he gave on the 21st of February and is now available on our YouTube channel, so it's probably a good idea to go and watch that first before listening to us. All episodes of Any Further Questions are available to listen to on Spotify and Apple Podcasts, so please do go and check them out now. Chris, how are you?
I'm all right, thank you. How's life? It's been a busy few months, but I'm excited to be back here talking to you and, hopefully answering a few questions.
Yeah, I'm really enjoying this series. It's really grateful for you to do this. Our first question, I thought I would kick it off with, could you just talk about radio astronomy? What is radio astronomy?
So astronomers are greedy for information. So we like to try and see the cosmos in as many ways as possible. And, of course, our eyes are only sensitive to a small fraction of the spectrum of light that's out there. We see our range of colours from red to violet, but we don't see infrared, we don't see ultraviolet, we can't perceive X-rays, and in particular we don't detect directly radio waves. So radio waves are just light but with much longer wavelengths, so wavelengths of maybe a few millimetres up to maybe even a few kilometres. And so in the early part of the 20th century, it was realised that if you built devices that were sensitive to these radio waves, then you picked up a background hiss which was coming from the cosmos. And so radio astronomy is the study of radio waves that come from beyond the atmosphere. And it turns out the radio universe is a complex one. It's full of all sorts of strange and bizarre objects, and it looks very different from what we can see with the light that our eyes can perceive.
How do astronomers differentiate between signals that may be indicative of extraterrestrial intelligence and those that have more mundane explanations, such as human-made interference?
One of the things I like about this podcast is we go very quickly into the hard questions. So one of the reasons that we're excited about radio astronomy is that traditionally we've used radio to look for aliens. The logic for that is sound. It's that you can transmit radio waves across the galaxy cheaply. So whereas optical light gets absorbed by dust, by stuff in the way in the Milky Way, we can see right across the galaxy in radio waves. So if you were deliberately broadcasting a signal to announce our presence here on Earth, you'd probably do it in the radio. And so we do use radio for SETI, or have done traditionally. But there's a downside, which is that to a radio telescope, the sky is a lot noisier than it is to an optical telescope. If you go out into a nice dark place in the middle of the night with the moon out the way, you have a dark sky and a few stars in the sky, and you can study and look at those stars. If you do the same with a radio telescope, even in the middle of nowhere, you see a bright sky full of all sorts of interference. Lightning storms produce radio waves, there's stuff bouncing off the atmosphere, and in particular modern technology, from mobile phones to communication satellites and everything in between, produces a lot of what we call RFI, so radio frequency interference. And so most of the things you detect with a radio telescope are noise. And that's a big challenge, particularly if you're looking for SETI, if you're looking for aliens. You tend to look for things like repeated signals at narrow wavelengths, and that's your mobile phone calling the cell. So we can get away from this partly by putting radio telescopes in the middle of nowhere. One of my favourite places to visit is Green Bank in West Virginia, where within I think it's a 30-mile radius, you're not allowed a microwave or a mobile phone, even if you live there. Luckily, it's fairly empty country. And we're putting telescopes in Western Australia and Southern Africa, where there are very few people as well. But mostly we do things like what's called chopping, where you point your telescope at the star you're interested in, and then 2 seconds later you point just to the side of it, and then you look back at the star and you look just to the side, and you do this. And the idea is that anything that's earthly will show up in both sets of observations, whereas anything that comes from the star will only show up when you're pointing at the star. So we use that sort of technique, and then we often try and use multiple radio telescopes. So if you've seen the signal in multiple telescopes, that increases your confidence that it's not real. But this can take a long while. I mentioned in the talk a candidate called BLC1, Breakthrough Listen Candidate 1. And it took 2 years from the detection of this signal that appeared to be coming from our nearest star, Proxima Centauri, to the point where the astronomers were confident that it was in fact noise. It was something made on Earth. So it's not an easy job at all.
Where is the best location in the world to have an observatory?
Well, we can answer this question generally and then for radio astronomy. So if you're a professional astronomer trying to build a telescope that you're going to use for research, I think there are sites in Antarctica that it would be very hard to beat. So there's a place called Dome Sea, which is sort of halfway between the South Pole and the coast. It's high up on the Antarctic plateau. Antarctica's a desert. It almost never snows there. It's just that when it snows, the snow sticks around. And so putting telescopes there would be amazing. It's clear a lot of the time. You'd have a 6-month night to enjoy the sky. Other than that, we argue about the Atacama Desert or Chile or Hawaii or La Palma. You want to be on a mountain near the equator, ideally up above water vapor in the Earth's atmosphere. For radio telescopes, things are a bit different. You don't need to be high up. Doesn't matter with radio. Probably equatorial position is useful because you can see more of the sky, but mostly we need to be away from people. And so Western Australia is pretty good. The density of radio telescopes is higher than the density of people out there at this point. And I think that's probably the best place in the world to be a radio astronomer.
Sticking on Australia, in New South Wales, Australia, there's the Parkes dish, and that was used to track the first moon landing. This person asks whether they weren't sure whether it was built specifically for this or whether it was just conveniently there to be used. So they're wondering if you could talk a bit more about the history of how the waves were measured, the obstacles which were overcome back then, as well as the uses of these discoveries today.
Yeah, this must be a question from an Australian. They're very proud of the dish in Parkes. So no, Parkes was built as a radio observatory. So it was built as a telescope, just like Jodrell Bank in the north of England was as well. And they were press-ganged into helping, essentially, with the Apollo landings. Normally, there's a network of communications dishes called the Deep Space Network that span over the globe that NASA and ESA will use to communicate with their satellites. But for something like Apollo, particularly because they were sending video, which hadn't been done before and was high bandwidth, then they needed a bigger dish. And so the telescopes got pressed into action. It's not the first time this had happened. Jodrell Bank had been used to keep track of Sputnik when it was launched, the Russian satellite that kick-started the space age. Actually, less keeping track of Sputnik, more keeping track of the rocket that launched Sputnik. So Jodrell had this sort of borrowed, almost semi-military use for many years, keeping track of missiles. So you can repurpose these things, but when you do that, you're using equipment that really wasn't designed to transmit video and broadcast it to the world. And so there were some hairy moments in getting the dish up and running. The communications to Houston went through a different system, but we nearly lost the video of the one small step, and it was only the astronomers at Parkes that managed to get their system back online and working just in time. So there's a famous movie called The Dish, which covers this story. It glamorizes it a little, but really it's about hammering complex electronics into place and hoping that they work. I think radio astronomy has the distinction that the dishes are pretty simple. Because the wavelengths are long, you can get away with imperfections on the dish, whereas for optical light you need a carefully polished mirror that has to be very accurate. For radio astronomy, you can sort of, and apologies to everyone listening who's ever built a radio telescope, you can sort of hammer the thing together. It doesn't really matter too much. But the complexity is on the receiver and the electronic side. So what you do with the radio waves you receive can be the most crucial thing. And really it's the rise of computing power over the last 50 years that have made radio astronomy quite so powerful. We're still using, for the most part, the dishes we built in the 50s and 60s, like Parkes, like Jodrell, but the computing on the back end makes them unrecognisable.
With the advancement of technology and the increase in satellites, does that make radio astronomy more difficult?
It does, for exactly the reason we were talking about earlier, that things are noisy, and noise from satellites is particularly disruptive. One of the problems that's happened recently is that there are actually bands. If you imagine tuning your radio, there are bands of frequencies that are reserved for radio astronomy that no one's supposed to broadcast in. So, for example, hydrogen in the galaxy emits at a wavelength of 21 centimeters, wherever it is. So if you tune in to 21 centimeters, or whatever the appropriate frequency is, you hear the hydrogen from the galaxy. And so there's a little window there that no one else is supposed to broadcast in. And most people try and respect that, so satellite operators will avoid using it and so on. But what's happened is that as satellites have become cheaper, in particular in the last 10 years, people have switched from the old expensive way of building a satellite, where you'd use only components that were space qualified, that were specially made for space, that were designed perhaps just for your mission, to a modern era where it's quite cheap to build a satellite and you tend to use off-the-shelf parts that you buy from Radio Shack or whatever the equivalent is. And some of those parts, because they're cheaper, because they're not as well tested, leak into these bands, and so they're beginning to really interfere with radio astronomy as the number of satellites in the sky goes up, and there are more there now active than there've ever been, and Elon Musk and others are lobbing 50 to 100 up every month. Then the sky's getting noisier, and so some radio astronomers, perhaps the most pessimistic ones, think we're going to need to flee the Earth, and there's serious talk about putting radio astronomy on the far side of the moon, where the moon would shield from the Earth. And it sounds like a great idea. It's the perfect place. The only problem is that the technology that makes it possible to cheaply build an observatory on the moon will also take other people to the moon for all sorts of reasons. And so we may only have a small window to go and put a radio telescope there before it becomes so noisy that we have the same problems that we're encountering here on Earth.
You talked a lot about Reba in your lecture you gave at Conway Hall. How did Reba manage to build a radio disc in his backyard?
Yeah, Reba is one of my heroes. He was sort of the second radio astronomer ever and the first to build what we'd recognise as a radio telescope, a steerable dish with an antenna to pick up the results. So the first thing to say is that he had deep technical expertise. So he was an engineer by training, and in fact that's what his day job was thinking about radio for communication. So he really knew his stuff. So he was coming with much more technical expertise, much more background than any of the astronomers of the day. And so, we shouldn't, in talking about him as an outsider and talking about him as a non-astronomer who was dabbling in this stuff in his spare time, I really don't want to give the impression that he didn't have expertise, because he did. He was much more qualified than the people who were judging his work. But as for the rest of the design, well, it looks a bit shoddy, it has to be said. It's sort of plywood and nailed together, and it does the job. But I think really the interesting question is, why did he think it was possible that on his own he could build a world-class observatory and map the whole thing? So how is one thing. The thing that's infinitely, I think, impressive about him is that at no point did he sit down and say, well, this is too big a task for one person. He just got on with it. And it took years. It took years of effort to build the telescope. It took years of effort to painstakingly map the galaxy and produce the results that he did, yet let alone winning the arguments with the astronomers to publish them. But there must have been something there that just told him he should get on with it. And in many of the other phases of his life, it was pretty clear that this habit of getting on with stuff, even if he's told not to, was a key Great Reba characteristic.
He sounds like an inspiration for budding radio astronomers out there.
I think so. I met somebody after the lecture, actually, who runs their own radio observatory, and there's still a bit of this culture of amateurs building telescopes and keeping an eye on things. Certainly, you could see it coming out of sort of the ham radio tradition as well. So that it's always been a sort of engineer's bit of astronomy, people who like getting their hands on kit and thinking about the technical details of things. And there's definitely a flavour of that in Reba's work as well.
If we were to pick up a radio signal from an alien, how might that inform us as to how advanced they are, other than that they just have emissions?
Yes, it's a really good question. Well, I think for the purposes of answering the question, we should ignore whatever the message contains, right? Because obviously it's possible they could be broadcasting, who knows, a mathematics textbook, instructions on how to build a device that will destroy us all, or, their equivalent of the Bible or some other holy book. So let's ignore the content of the message. I think we get some sense of their sophistication by the strength of the signal. I think I'd be interested in knowing whether it appeared to be targeted towards us or broadcast into the cosmos. If it's targeted towards us, we know that they're sophisticated enough to have identified that this is at least a likely place that life might exist, which tells you something about their astronomy, I would think. But it's going to be very difficult. I think just the fact of a signal will be a big thing, and then the details are going to be hard to fathom. I think one crucial thing will be whether it's a one-off, whether you see a repeating signal, whether it's coming from multiple places. One of the interesting stories that I told in the lecture was Jocelyn Bell Burnell's discovery of pulsars. And I mentioned, I think, that when they found the first pulsar, they called it LGM1, partly tongue-in-cheek, this idea that it might be a little green man talking to them, because it was this apparently unnatural, rapidly repeating signal. And the story goes that they were very relieved when they found a second one, LGM2, because they thought it was a apparent coincidence that aliens would be communicating in the same way from different bits of the galaxy. And, pulsars turn out to be natural. They're not aliens. But I'm not sure that logic holds, actually, because if we discover a civilization that's transmitting into the cosmos, we should expect maybe an intergalactic network, right? We may be just the latest to subscribe to intergalactic dial-up and get online or whatever else. And so I think whether there's one signal or... once we know what kind of signal we're looking for, checking whether it appears elsewhere in our data becomes much easier. It's much easier to find things might be there. And so, one thing, are they on one planet or have they spread across the cosmos? That would be an important thing to answer fast.
Is it too far-fetched to say that it would be mathematical in nature? I watched Contact, the Robert Zemeckis film.
I love Contact. It's brilliant.
Yeah, and in Contact, I think is it prime numbers?
It's prime numbers to begin with.
Yeah, which is interesting. An interesting idea.
Well, the idea is it's an unambiguous way of showing that you're not there. Natural. Yeah, exactly. The thing about Contact that doesn't make any sense is that the signal changes pretty quickly after they detect it. So, how did they know they were going to be fortunate and detect it in the first few minutes?
Let's do another podcast about Contact.
I'm happy to talk about podcast. Contact was hugely inspirational to me when I was growing up because it showed astronomers doing astronomy. There's this wonderful scene. Here we go. We could do the film podcast now. But there is this scene where they're sitting in the control room of the Very Large Array. They just see this signal. And it's the most realistic panic in a scientific environment I've seen on film, because they're suddenly like, hang on, there's a signal. Are you recording it? Are you checking that it's real? Have you left something switched on? And then they realise it's coming from Vega, and they start going, well, hang on, Vega's a young star. It's got a debris disk. How could a civilization survive? And then they get back to just recording the data. So you can imagine what would happen if we did find a signal.
I have heard that it's very famous for being loved by scientists and astronomers because of how accurate it is. Apparently the billionaire character in the film, the billionaire who comes in and finances
provides
things
the money,
and provides the money, back then in 1997, it's become so true now, and it's sort of so relevant and so accurate.
Yeah, there aren't many films that show the scientists pitching for cash, which is a large part of what we do. So that's true. The book is better. Okay, in my opinion, or at least the book has a twist at the end that's missing from the film.
Right. Okay.
That changes, I think, how you feel about the whole ending. So I won't ruin that for you or the listeners, but
I'll read it.
I mean, the other thing about Contact that comes up a lot is that Ellie Alloway, who's the character played by Jodie Foster, sits on top of her car in the desert listening to data from the radio telescopes, and no one does this. And no one does this precisely because of what we were talking about earlier, because it's noisy. Yeah. Right? It's not silence. You're thinking like an optical astronomer. You think silence and then this bleep with prime numbers. Actually, you've got signals going all over the place. It's hidden. I've listened to radio data in an effort to sonify it, and it sounds horrific. So no one does that. So there is that inaccuracy as well.
Go and watch Contact if you haven't seen it. It's a wonderful film. I'm going to read the book. Your other part of your lecture was about pulsars. If you could just first talk about what a pulsar is, and then we'll get into the questions that we had about pulsars.
So for an observational point of view, pulsars are objects that send very regular, very fast pulses of radio waves towards us. So they can be as fast as milliseconds, so we get thousands of pulses a second. Some of the slower ones might pulse once every few seconds. And when they were discovered, as I said, it wasn't at all clear what they were, but that rapidity gives you a clue. So there's a rule that if things are changing fast, they must be small. And that sort of makes sense because you have to coordinate. If something's changing to cause a flash or something like that, if it's changing rapidly, then it must be a small thing. Otherwise, you can't get something the size of a solar system to change in unison every second. There's no physics that can do that. So they realized these were small, compact objects, and they'd actually been predicted. So when a star a bit more massive than the sun reaches the end of its life, it loses its outer layers, but the core becomes this hugely compact thing called a neutron star. So you can think something like the mass of the Earth compacted into something the size of a city. So a teaspoon of neutron star material is really heavy.
Yeah.
Right. Very, very heavy. The analogy starts breaking down. But they're these compact objects, and they retain the spin from the star, so that's why they're rotating quickly. And they also have magnetic fields inherited from the star. And those fields can shape powerful jets of material that come away from the rotational poles of the neutron star. And so as they spin, these jets whiz round. And if we're in the right place, we experience it as a sort of lighthouse effect. So we see a flash and a flash and a flash. And those are the pulsars that we see.
When a pulsar's beams point towards a particular planet, how does the electromagnetic radiation it emits affect the said planet?
So by the time we get here, often the animations of these things look very dramatic, right? Because you have this bright cosmic lighthouse sweeping across us a few times a second. Actually, pulsars are far enough away, and the radio waves are at long wavelengths, so there's no discernible effect on the planet whatsoever, other than that if you build a radio telescope, we can detect these things and then use their timing to inform us about the cosmos, because we've got this galaxy filled now with natural clocks.
Can you elaborate on the significance of the discovery of pulsars and their role as cosmic lighthouses? How have pulsars been utilised in astronomical research beyond their initial discovery?
So studying pulsars has been fascinating, partly because they're weird objects, right? So how do you get the mass of the Earth and crush it down into something the size of a city? It turns out, for example, that they do things like occasionally glitch, so they almost miss a beat, or they suddenly change in their period. Not very often, but that's presumably to do with some change in the structure of the exotic matter that lies beneath the shell of the neutron star. So people study things like that. But I talked a bit in the lecture about their use as clocks. So one example is the famous double pulsar system, which is a pulsar in orbit around a neutron star. So there's a pair of these things. And what we can see, since it was discovered since the 70s, is that they're slowly spiralling in towards each other. I think the time that they take to go round is now a few seconds shorter than it was on discovery. And so that tells you the system must be losing energy. And what's actually happening is the motion of these two massive objects are causing space itself to ripple in what we call gravitational waves. And these waves carry energy away from the pulsar system. It's a prediction of relativity that we can then test with the pulsar system. And Hulse and Taylor, who discovered the thing, won the Nobel Prize in, I think, 93 for having the best test of general relativity. So then we can go up another level, another scale, and people have spent the last 15 years monitoring many pulsars across the sky in what's called a timing array. So you just keep track of these clocks that are ticking away, and you look for periods where pulses arrive slightly late or slightly early. And then you look for correlations across the sky where that happens not simultaneously but close in time across many pulsars. There's a mathematical way of doing all of this. And when you do that, what you discover is that there is a systematic effect. And what that means is that space itself is rippling. So we're living, if you think of us embedded in space, or space-time if you want the technical term, which you don't, we'll stick to space. But if you think of us as living in space, we think of space as a neutral actor, like a flat stage that we move through and around and in. But actually the whole thing is choppy. The whole thing is moving. We can now measure that using these pulsar timing arrays. That was a result that just came out last year. And I think that's really exciting, this sort of sense that all of the dramatic events that have happened in the cosmos have contributed to these background waves, and we're now at the point where, using these pulsars, we can detect some of that background. It's a kind of beautiful result, I think.
How has the JWST changed things?
So JWST is useful because it's an infrared telescope. Part of its use is it, again, gets us beyond the optical and into the infrared. You don't see pulsars particularly in the optical, let alone the infrared, and so they haven't quite connected. One way that the two instruments collide is this result I was just talking about, which was these background gravitational waves. One of the ways they could be produced is by the merging of very massive black holes in galaxies across the universe. And JWST is starting to tell us about the population of black holes that exist. So there's all sorts of crossovers, but I wouldn't say yet that there's one result where we can say, yes, the radio astronomers have done this and JWST has done that. We'll get there, but we're all busy playing with our new toys on our own at the minute.
We had a question about FRBs, fast radio bursts.
Yeah.
What are FRBs, firstly?
Good question. So again, I always like, in the radio, I think it makes sense to talk about what we're seeing and then what the explanation is. So what we're seeing is exactly what it says on the tin, a fast radio burst. So these are rapid, maybe a few seconds, maybe a little less, bursts of radio waves that appear at different frequencies. They come from all over the sky, and some, but not all of them, seem to repeat without any pattern. So they sort of randomly pop off every year or two. We know that at least one of them lives in a distant galaxy because we've seen the galaxy, but for most of them we're not sure. But we think that they're distant things. So now we need something that explains distant bursts of radio waves. And at the minute we're sort of at the waving our hands kind of explanation, but we think it might be to do with the neutron stars again, these things that cause pulsars. One possibility is that if you collide two neutron stars together, you might get something like an FRB, but we're really at the early stage. We've only, until the last few years, we only had a few tens of these things hidden in the data, and we're now up to thousands, and so we can begin to sort them out and work out where they happen and why they happen and how powerful they are and so on.
What are the challenges, or are we just in the infancy of research?
I think it's, again, looking for changing signals in a noisy environment is really hard. So the first FRB was found in archival data many years after it was taken. So it had sat there for not quite a decade, but for years, waiting for somebody to notice it. Because unless you're looking very closely, lots of these things look like just noise. And so getting used to the changing sky is just really tough. I have a lot of respect for people who deal with radio data. It's not an easy task at all. This
person who asks this question hopes it's colliding black holes, exotic particles, or even potential extraterrestrial sources.
Yeah,
possibly.
so colliding black holes are a possibility, although how you generate a burst of radio waves from that is hard. Exotic particles, sure, that's a good guess as anything else. ET, well, maybe. There was... I'm reminded slightly of gamma ray bursts, which are very high energy bursts of radiation that we see. One potential explanation for that was the flash of light from starships as they transition to faster than the speed of light. You'll remember from every Star Trek credit sequence. I don't think we need that explanation just yet.
It used to be Pluto as the question that was asked after every single one of your lectures.
No, I didn't get Pluto in. I had a way to get Pluto in, but I managed not to be rude about Pluto in this lecture. So.
Now it's someone who is asking about the Mysterons and mentions the Mysterons in every one of your questions, which is quite funny.
Good. Well, I didn't work them in, but perhaps their presence was felt.
Possibly. Could you explain further how the discovery of the BLC1 signal around Proxima Centauri unfolded and what steps were taken to investigate its origin?
So this was this signal that was the best candidate for years that we've had for an actual SETI signal. So it was obtained by the Breakthrough Listen program. They were monitoring our nearest star, Proxima, precisely because they were looking for signals that might be indicative of life or intelligent life there. And the first thing they did was check that the signal only appeared on the star, not off the star, which it did. They looked at its frequency and how it's changing, and it was consistent with coming from the distance of Proxima. And then the thing that makes it really convincing is that it was slightly... You can think of this as velocities, right? So what we measure is whether the source of the signal is moving towards or away from us. And we found that it was moving a little with the star, but slightly offset. And that's exactly what you'd expect from a signal coming from a planet around the star. So, because the planets, of course, orbit the star, so you have the velocity of the planet to worry about as well. So that became really exciting. So that was the point where I think it was named as a candidate and people got excited about it. The next thing that happened was that they went and observed it again. It was found in archive data. They went back, looked at the star, didn't see anything. And for me, the lesson to take from this, more than anything else, is that we've got to be faster at finding these things. Because if you can find it as the data comes off the telescope, you'd immediately go back and keep recording data. Whereas if you go back 6 months later and there's nothing there, you run the risk of having missed the signal. The other most famous signal in SETI history is called the WOW signal, which was discovered by the brilliantly named Big Ear Telescope in Ohio. And it's WOW because the person who found it literally wrote WOW next to it. It's this very strong signal that came from a random patch of sky, but was never repeated. And so it's not clear what to do with the WOW signal. It almost certainly was noise, but it could have been real. But even if it was, what's there to say other than it existed? I guess you say wow once and move on. So we should have been faster. We weren't. It disappeared by the time they went back. And so they went back through the archive. And instead, normally we look for signals that might be interesting. And we do our best to do that algorithmically. This time, given that they knew what the signal looked like, they looked through the whole archive for signals that were the same shape and same frequencies as the BLC1 signal. And that's what killed it. They found similar signals while the telescope was pointing at other parts of the sky. And so at that point, they said, okay, this is probably some local interference, and that closed the case. But it's a really good case study for how it took about 2 years of work. It took about 3 separate papers needed writing to do this. It took a lot of negotiation, and we still can't point to the culprit. I can't tell you which satellite transmitted as it went over or whose microwave was malfunctioning. But I think the fact that it's appearing randomly in the data tells you it's local interference. But it's a nice example of all the steps you go through to try and see whether this is real. We've just got to get faster at it.
I think I have seen the image of WOW being written in pencil with an exclamation mark.
That's right. It's a piece of paper with numbers on,
yeah,
which is the printout from the signal, and then he circles it and writes, right, it's Jerry somebody. Who wrote a really good essay about 20 years later that said, stop saying this was aliens, we've no idea what it is.
The reason why I've seen it is because I think a previous Gresham professor of astronomy, Catherine Blundell, talked about it in one of her lectures.
Right, okay.
I can't remember which lecture, but if you go back in our archive and look at Catherine's lectures, you'll find it. She talks more about it there. Could you provide more details about the square kilometre array and its potential contributions to radio astronomy? How will it advance our understanding of the radio sky?
Well, it's a great question to ask today because I've just seen that they've just started the Australian half of the array. So the first antenna is now in the ground, which is really exciting. So SKA is this massive international project. Telescopes in South Africa and Australia, headquarters in Manchester. About 8 countries so far signed up to participate. And it is the last radio telescope we will ever need. So it will be powerful enough and big enough that it will detect radio waves from every galaxy in the observable universe.
How can you say that with such confidence?
Oh, well, I'm probably, I'm going to look very silly when I come and ask for money for another one. But it's big enough that we will detect all galaxies in the universe.
Okay, yeah.
So we'll get the deepest view of the universe we've ever had, which is really exciting. And of course, it will look for transients and find thousands of pulsars and everything else. The name SKA comes from the collecting area of the dishes. So it's made of many, many different dishes, which are all wired together, but collectively will head towards having a square kilometre. What's really exciting about it, I think, is that building a radio telescope isn't like building an optical telescope. In an optical telescope, you need your mirror and your whole telescope there before you can do anything. Because these radio telescopes are made of many thousands of dishes, you just start observing as soon as you've got a little bit of it on the ground. And so there's already a telescope called Meerkat in South Africa, which is about 1% of the SKA, and it's taking what it's done is it's turned radio astronomy into an imaging science. So we now get these reconstructed beautiful images of things like the centre of the Milky Way, which show complex structure that we've never seen before, that show there's strange stripes of material and big balloons of inflated hot gas that have been driven by activity around the black hole. So we're really getting this view of the cosmos for the first time, even from what we've got already. And we don't yet quite know what to do with that data. We're still disentangling it.
Are there any alternative methods or technologies that have been considered for communication with extraterrestrial civilizations?
Yeah, this is a really good question. I said that we've traditionally thought about radio and SETI and looking for intelligence because of this ability to transmit over large parts of the galaxy. But who knows whether that's actually how aliens think? And in particular, I think the idea of radio as a natural communication method looks a lot less obvious in 2024 than it did when these ideas were first being mooted in the 1960s. Back then, you could tell the story of the 20th century as an increasingly radio-loud civilization. We'd gone from local broadcast to national broadcast to the beginnings of communication across continents using radio. And so it would have made sense that aliens would communicate by radio. Now, of course, we communicate by fibre optic cable and by narrow beam transmissions to satellites. So it's less clear that we will remain a radio loud civilization. So thinking about other things is definitely a good idea. Partly, this has led to a huge effort on what people call techno-signatures. So can we detect the traces of alien life without a communication? Can we see effects on a planet's atmosphere? Things like floating solar panels, or maybe how a very advanced civilization might affect its stars. So you can think of that sort of looking for aliens. But if we're going for communication, one promising area, I think, is to think about laser communications. To think about optical light being used. It has the advantage, it doesn't go as far as radio, but it has the advantage you can transmit more information because, as we know from fibre optics, you can flicker the light faster and you can get more information in there. And so people have started to search the sky for rapidly changing optical sources, maybe something like a pulsar, but in the optical. If we found that might be a sign that we've hacked into a laser communications network, but no luck so far.
How does redshift affect radio astronomy?
This is the effect that the expansion of the universe has as light moves through it. So as the universe is expanding, as light travels through it, then things get stretched. And so you end up moving to longer wavelengths. So if I send a blue light into the cosmos, over time it will shift into the red. Same thing happens with radio waves. Shortwave radio becomes long wave, basically. The one way it manifests itself, particularly in radio, is that I said there's this strong signature in our galaxy that hydrogen emits at 21 centimetre. For other galaxies, that will be redshifted. So the further away the galaxy, the further from 21 centimetres you get. And so what you end up with is a forest of lines. If I just look at a random patch of the sky, each galaxy contributes its hydrogen signature, but at a slightly different wavelength. And so you get this distinctive pattern of a forest of lines that tells you about the whole history of the cosmos.
What are the key insights and findings that we've had most recently? And this person mentions the meerkat in South Africa.
Yeah, I think that sense of complexity at the centre of the Milky Way is one. So that ties, I think, a little to the Event Horizon Telescope, which used telescopes from around the world to show the disk around the black hole at the centre of the Milky Way as well. I'd also maybe point to some work one of my students has been doing. Alex Anderson's been looking at transients, things that change in the sky using Meerkat, using a Zooniverse project called Bursts from Space. So if people are online, if you Google Bursts from Space and Zooniverse, you'll find it. And we're beginning to see that the radio sky, just like the optical sky, is transient. As well as pulsars, there are things that flare. We see the flickering of material around nearby black holes in nearby galaxies. And so I think we're learning the radio sky is a richer place than we imagined. And that's really exciting.
Thank you very much for joining me today, Chris. That was all the questions we had. And thank you at home for listening. And thank you for sending in your questions, if that's one of your questions we just answered. Your next lecture is on the 29th of April, called Is It Aliens? The Most Unusual Star in the Galaxy. Could you tell us a bit about that lecture?
Well, I'd start by saying it isn't. So if you have a lecture title with a question mark, the answer's always no. But this is a discovery that we made many years ago with the help of volunteers from the Zooniverse, which was a star that was behaving like no other star. And for a long while, the most likely hypothesis was that there were aliens building solar panels around it. So I'll talk a bit about that star, a bit about what it means to search for intelligence, and also a bit about how planets form and how we end up with such systems in the first place.
That's at Conway Hall in central London. So if you can come along in person, then do check our website for tickets. I believe tickets are still available.
They are.
So go and do check them out. And if you can't, then we'll be live streaming that lecture, and it will also be available on our YouTube channel. Chris, thank you very much. And I'll see you again in a future podcast.
Yes, pleasure. See you in a month or two.
Thank you.